Hello world, hello world. There it is. Okay, I always gotta wait that 5 seconds delay from when the clock actually shows up. Hey everybody, good to see you. Welcome once again to another edition of Fun and Games Friday of our distance learning live streams here at Learn Math with me, Brian Sapinski. I am ready to go here to get some good math help going. Brianna is in the background, sitting there on the couch. I will get her off the couch in just a second and to join us and stuff like that. She's in there somewhere here. Hi. Hi. You gonna come over here and you can't stay back there. We can't hear you over there. So, no, don't yell. Get up. It's, you know what it is? 9 weeks of sitting on these small wooden chairs that we've had from some kind of like kiddie table and chair set that Brianna had when she was little, and then Joey kept the chairs and stuff like that. And we needed something that was low to the ground so that we could be able to be at a viewable height compared to where everything else is safe. It's all strange, but you get the idea. All right, you guys know what to do out there if you're watching, and hopefully a friend of the channel, or I hope that he's a friend of the channel. I hope he's watching from way far away, wherever that he is, and he's getting his buds over here and stuff like that. But regardless of that, and whoever it is that's watching there, boom, there's the live chat to the side. Submit topics right there. Anything you want us to take a look at while we come up with some stuff and play a game or two here on this Fun and Games Friday. And then so submit in live chat or brian.sapinski@gmail.com. We'll go over whatever it is that you like, anything in the K-12 spectrum here. Okay, but to start off with, and to kind of build off of another brilliant picture that Brianna has drawn and designed as the logo for today's stream or whatever. And she does, hey, Brianna, I need you because you got to see the picture here. If you don't see the picture I'm drawing, it's going to be very difficult to do. You're not going to be able to see it. What happened? You should have done that already. Oh, dear God. She's doing this to me already. I'll set the drawing in place while we got that in position here. Okay. Had it on a recent live stream. I talked to you guys about this. We talked about the circles, and we talked about the different things about a radius, a diameter, like the one I have drawn there, chords, yeah, any segment that has 2 points on the circle, all that business. However, I want to focus specifically right now on radii and diameters, because when you have several of those drawn in a circle, you can actually create angles using two of the radii, and that actually sort of what we can do right there is, so here I'll draw a few of them just for example there. Okay, so kind of, and you know what, this kind of also goes in theme of when we had the when we were talking about the pie charts last week too, the circle graphs, which if you haven't already seen it, we did reshoot that very garbled live stream from from last week, and we reposted it Wednesday morning and stuff like that, a little later than I would have liked, but that's okay. It happens. We've been there, but it's there. It's all nice and clear and in order, so you can actually read it and watch it and know everything the heck that we were talking about without any skips. So be that as it may. So you've seen us do this, okay? And we talked about when we measured these angles, when we were coming up with the wedges of a pie chart, we saw we did the protractor to actually measure these. But now let's suppose that we actually get let's suppose we have the measurements given to us right at the start. Like let's say we have an angle here representing 50 degrees inside of the circle. Now, the thing is that in addition to these angles, what it does is, aside from taking out a wedge or a sector of the pie and stuff like that, what it does is that this angle, if you follow the lines, it actually captures a certain part of the circle right here, like this. It does that kind of thing. This piece, which is the kind of the main focus of the drawing that we put in the in today's advertised picture. This is an example of what is called an arc. So arc similar to arch in its nature. So like you might think of some things that are kind of similar to this or whatever. Like you think about the Gateway Arch in St. Louis. You know, that bit the big monument that they have there, where it's kind of like this. Although the arch in St. Louis is more like a parabola than it is an actual thing, but the general idea is the same, that it's got some kind of a curve where it's like a portion of a circle or an oval. So call it whatever you will. That's what you can kind of base that on. But that's exactly what we have in a circle right there. Now, the thing is that this arc has two different measurements that we can associate with it. There's a degree measurement that's associated with it, and there is also an actual physical length that there is to it as well. I want to talk about the angle measurements first, because those are the easy thing. The idea here is that this 50-degree angle that is originating from the center of the circle, because of the fact that this is the center, we call this 50-degree angle, borrowing from the word center, we call it a central angle. And the nice thing about it is that whatever degree the central angle is, the arc that it captures is going to have that same degree measurement. So if I give these two a point here, A and B, nice Brianna was here in the room at the moment for me to bounce it off of. I'm lonely here, folks. Help me. So, here, wait. Shoot, darn. Nobody's in the room. But the point is that like if this central angle, and I'm just going to put the letter O here just to emphasize. So the idea would be if the measure of angle AOB is 50 degrees, that means the degree measurement of arc AB is also going to be 50 degrees. So that's what we want to be able to see from that. So that's going to be the big thing that we're going to look at. Now, as soon as I get Brianna back in the room, what I want to do with her is that I want to try to find measurements for these other three central angles and thus the arcs that they capture. Now, we're going to find some other measurements along the way of other arcs, not just the ones created by these pi wedges and stuff like that. So here, I'm going to put a C here. I'm going to put a D here. Okay, and I'm going to put one other arc measurement. Okay, so here, I'm just going to take the center point O out for a minute, because I don't want it to be too distracting for Brianna or for you guys. So let's suppose, okay, how's about, let's say that I give this angle COD and thus arc CD. Okay, so let's say if measure of angle COD, let's say, is 80 degrees right there, that means that the measure of arc CD or DC, it doesn't matter which way you call it, would also be 80 degrees. Okay, so the first thing I'm going to ask Brianna when I can get her back into the room is I'm going to ask her about the other two central angles and the arcs that they capture. I want to find out what measurements those are, and I want to see if you guys know too. All right, because again, you want to keep in mind here. Let me fix my 80 there because it's a little, so you can actually read it. Hello, there it is. So the thing you want to recognize is there's two main facts you want to keep in mind for yourself. Number one, you want to recognize that you want to know how many degrees a full circle has. Hopefully you know that by now, because we've even talked about it in the last couple of shows. And then also at the same time, here's the thing. This AC, you've got a diameter there of that's written right there. And the thing is that You know that the diameter, if you go from one point to the other ends, if you went around the circle or whatever, if you think about it, this goes halfway around the entire circle. So if you know how many degrees the full circle is, then you know that the diameter is going around the arc from point to point. Diameter is going to be half of that. So think about those two numbers. If you know what they are, here, punch them into the comments. You'll play along with us while we go. And where the heck is Brianna? I'm just talking. Because see, this is the problem. I've got nobody to interact with here right now. I've been left all alone. I'm talking to myself. We are live. I can't stop. This is getting all crazy here. Kitty, you got to save me here. I have no one to banter off of. What is that? She picked now. Okay, well, I will hear. Can you help me banter off this? Wait. Answer this question. Here, sit for a second. Just please, come on, help me. Besides, you lost your time last week when that one got garbled. Here, sit for a second. No, come on, help me. Say hi to the people.
Hi.
Well, get on camera. They like seeing you.
No, hi, people out there.
Get over here.
No.
I've never met somebody so camera shy in my life. Come on.
No, she's good. Or he's good.
Oh, fine. Okay. All right. Just answer this question for me first. Okay. All right. Circle. How many degrees in a circle? I know you know that. Like, no, the whole. No, more than that.
360.
Okay.
Oh, 360.
All right. So you know.
360.
All right. So you know that the full circle is 360. Okay. So now here's the thing. Then the diameter there. So if the whole thing is 360, for the diameter, how far around did you go?
180.
Halfway. So the diameter will lead to a 180-degree arc. So here's my question then. If I know that if arc AB is 50 degrees, so follow the AC's diameter. If this is 50 degrees, how much is arc BC going to be? Yes, okay, it's going to be 130. Okay, and over on the other side, what's the measure of arc AD?
2.
No, look on this half of the pie now. Look at I gave you part of it. How much is missing on this side? 100 is, yes. Okay, got it. Take the 80 off of the 180. Okay, so now we got those, and so you can put all those in place. So now you've got all the individual wedges going this way, that way, and the other way. Okay, now let's take it a little step further here, because all these these individual wedges that we got and the names that go with them, I'm just gonna take the central angles out of the conversation for a second. All these that are direct paths from one point to the other, direct like that, 2-letter arc names. These are all examples of what are called minor arcs, okay? And we also refer to them as minor because of the fact that they are all less than 180 degrees. Now follow this, okay? Because now we're going to extend upon this a little bit, make a little bit of a puzzle. Okay, I said at the beginning that AB, that the arc AB directly from AB was 50 degrees. But what about if I wanted this arc? What if I wanted the measure of arc, let's say ADB? Now, this is sort of the same as this. I say sort of because you got to start at point A and end at point B, but you have to hit D somewhere in the middle. So if I start at point A, in order for me to hit D first, which way do I have to circle around? I have to circle this way to the left, so I have to come all the way around and then stop at B. So now, what's the total degree measurement that I went all the way around?
310.
It is 310. Yes, you can look at it one of two ways. Either add all of the individual wedges that you got along the way, or since it uses everything but the 50, take 350 or take 50 off of 360. So either way, that's 310 degrees. That's an example of what's called a major arc, because the fact that it's bigger than 180. And if it's 180 exactly, since that's halfway around the circle, that's what we call a semicircle. All right, so let's play off of that a little bit. Okay, so how about what about the measurement of?
Oh, Hans has a question.
Oh, hey, Hans came in. How you doing there?
Look what
good,
I have resorted
good
to,
to see you
Brianna.
back.
A
Yes.
Yoshi toy.
Yes, she saved you while I was stuck in no banter lands.
Hi, Hans. Thanks for joining us.
Yes, he's our friends all the way from the Netherlands watching us. He came in on Tuesday and was joining us there. That's my wife trying to save me while Brianna was detained temporarily. Okay.
Hi. How's the weather?
Yeah, how is the weather over there? We just finally
hot.
hit our hot streak. We went from 50s and 60s like the last couple of weeks or whatever, mostly 50s, and now we're in the mid 80s today. It's crazy. What's the weather like in the Netherlands today? Let us know. I'd love to hear how the difference is. Okay. Well, here. Answer a couple more for me while we're here, just to finish the topic here. All right. So take a look at this one, Keith. What about
Yoshi.
Okay. What if I wanted CBD? So now you got to start at C, pass B along the way, and stop at D.
280.
280, right? Take the 80 out. This is the only part you don't use. Take the 80 out of the 360, and you get 280. Okay. All right. What about what about if I wanted? Okay. Now follow this. What if I wanted the measure of arc DB? Now, it's only two letters. Now it's not two letters that are next to each other though. But what it means is that if they give you two letters, it has to be the direct route. So
150?
Okay, it would be the 150. You have to compare both directions, and if it's just two letters, you automatically take the minor arc, the shorter one. So the shorter distances, you got 150 this way versus 80 and 130 this way. So the minor distance is 150. If you want the major one, you would have to throw in a third letter, and so that would be DCB. So what is it? So what is it the major way? Oh, we got more questions here. Oh, good. Yes. Oh, yes. Good. Yay. He brought friends. Yay. Great. Good to join us here. Okay. So real quick, give me the major one real fast. So DCB.
260?
Oh, wait.
No, wait.
Wait, you went too far.
Oh, I went too far.
DC and stop at B.
Oh, wait.
So DC and then to B.
210.
Yeah, that's it. 210.
Oh, okay.
Yeah, because it would be these two.
Oh, okay.
Yeah, because remember when you did DB directly, you went this way and you used these two.
Okay. I got it.
This still starts at D and stops at B, but it has to pass the long way around through C, so it has to use the other wedges. So that would be 210. Okay, so you did just fine there. See, you can jump in on this sometimes. It helps me out.
Okay, answer their questions.
Okay,
Bye.
all right.
Have fun. He'll help you.
So I hope that makes sense in terms of circles. I want to come back to this a little bit later to get some more discussion and stuff like that. So we'll play along with that more in a little bit.
Friend. Hi. I hope it's not as hot here as it is there.
Get your whole face in there. So see, that's my wife Andrea, folks. Thank you, cutie.
You're welcome.
He helps me out a lot. All right. Okay. All right. We'll come back to more of the circles in a little bit because I want to talk about the arcs in relation to air into circumference and things like that. I want to get into that conversation a little bit too and help out some of my geometry guys. But in the meantime, we got some questions from our Dutch friends across the pond, as Strong Bad would say. Where did I put my phone? I had my phone there, or my calculator's over here too. There we go. So we got that there. Hello there. Okay, good to see you. All right. Okay, let's see what we got. Okay. Okay, how to do logs on the calculator. Okay, I remember we talked about this a little bit the last time you came here, Hans. We want we wanted to discuss that. And like I said, I've got my my TI-34 handy and stuff like that, and everything there. Okay, we had discussed. Okay, all right, we'll get a couple of different things in there. So we see. Let's here take one thing at a time. Okay, so calculating the logarithms. All right. Now we talked before about within most calculators themselves, you have to deal with the principle that the calculator is only going to handle two kinds of bases. It's only going to handle the standard log 10, which it's not going to show that automatically. It's just going to say log, or it's going to calculate the natural log, which is the log with that natural number e as the base. If you need to do any other one, we talked about that change of base formula last time that you have to do. So, and we'll get to that one in a minute. So for example, here let's just use the standard one just for a second. So if you're calculating, for instance, the log of 1 million, for example, all right, you just have to literally punch it in like this with on the calculator like so. So for instance, on the TI-35 here, okay. So on the TI-35, I would be hitting to get to the log. You notice it's in yellow here. I don't know how well you can see that, but right there above the pi sign, you see log written there in yellow, LOG. And stuff like, yes, thank you, please, yes, okay, we could definitely use the pitch, so please share along with us. Okay, so I'm going to hit second pi, and that's going to queue up the log menu so you can see it right there. Okay, since I'm calculating a logarithm, log is underlined, so I'm going to hit enter on that. Whoop, hold on a second. Whoop, I hit something else on accident there. Okay, there, enter, there it is. Okay, and then inside the parentheses, you're putting the number that you want the log of. Because remember, what we said this reads as in an exponential form, the inverse means that we're looking for 10 to some power equals 1 million. So we're trying to get our way back to that exponent there. So when we type in the 1 million, whatever it returns to you as a whatever it returns to you when you hit enter, that's the exponent is that you're looking for there. So we punch that in, and in this case, you should see on your calculator, you should see a 6, Hans, that you should get out of that when everything is said and done. Okay, so that's the type of thing that you're looking for there. Okay, now same idea. If we're looking for just to throw a couple out there. Now, if you're looking for one that isn't a power of 10, like if you're looking for, let's say, log of 50, if you punch that one in, okay. Now this time you'll see it's going to give you some irrational exponent or whatever, because you can't multiply an exact number of 10s by themselves and get 50, because if you multiply 2 10s, that's 100. It's already past that. So you can see the result there. It comes out to about 1.7, or okay, 1.6989, so on like that. So we'll call it approximately about 1.70 would be the exponent. So it would be something in that nature there. So that's how we read an exponential form. Hello, Jan. Good. Welcome aboard. Glad you could join us there. So that's the nature of that. And we also talked about that if you go to do any change of base forms, if you want to do logs for anything else other than a log 10 or a log e, we talked about that just to show the change of base form again. Log of x that leads to y would be based on punch this into the calculator, be the standard log of the y that you're trying to reach divided by the standard log of the x that was your base. So here, Brianna, help me out with this setup here. So if I want to punch this into the calculator, if I want to punch in log 3 of, actually, let's do this different one. Okay, log 4 of 256. Okay, So following this form, match the numbers up with the letters. How would I have to write the change of base? Yes, I do, Vincent. Yes, welcome aboard. So here, follow along with this. So how would I have to? So how would this part read up here? Look at what numbers in the Y position. What numbers in the Y position up there? You can play. You guys can play along in the chat as well. So reading in this one, Brianna, what numbers here? What numbers here in the Y position up here? Match it up. But the whole thing. The whole thing. That's not just a 2. Okay, so this would say log 256 over what would be on the bottom. How would the bottom read? What's your other number? What number's here? So, yeah, so log 4. Come up and join us. Sit down. Sit down. Play along here. All right, so that's how you. Yeah. I'm glad I got some good PR there. I thank you guys for that. Okay, so to enter that in on the calculator. Okay, so that's how we would enter it. So we would put in. Okay, I'm gonna hit second pi. Hit the enter on log. What? Why is it doing that? Okay, 256. Close the parentheses. Divided by, again, hit second pi. Hit enter for the log and punch in 4. Okay, you can't see the whole thing on mine there, but it's in there somewhere. If I scroll it all the way through, you'll see it in there. And if you hit the enter on that, and you'll see it gives you exactly 4 as the result. And that's naturally what this would give you in the first place there. So that's the way you want to put that into position there. So very good. Okay, Brianna.
What?
Mommy does that because she doesn't like being on camera. Okay, come on. You're fine with it. Could you sit down? Okay, you can hold the unicorn, but sit down here. Join me on camera here. It's been weird talking to myself this whole time. Okay.
Unicorn.
Feel free to pitch in more questions, Hans, if you like there. Okay, so that's how you would enter it into the calculator in any other circumstance. Again, I'll just show that last one the long way. This is how it ends up reading the calculator. Log 256 divided by log 4, and then hit the equals key, and it should return the 4 once you hit all that. Okay. Again, where the log function is, it's going to be different from calculator to calculator, so you find it appropriately where it is that it lands there. Okay, but that's the way in general that it would read. Okay, so so let's see what else we got here. Okay, let's see what other suggestions we are getting. Yes, there's a lot of you in there. Yes, I thank you. I thank you for joining us in there. Do you have a topic you'd like us to do? Please bring it up there.
We have unicorns.
What?
We have unicorns. See? Unicorn.
Okay, well, what's that got to do with anything?
Unicorns.
So let's
unicorns.
Okay, but I need a math topic. I can only do so much with that. Okay, let me see here. Okay, wait. What is the okay. All right, because I got a couple of questions here. Okay. All right, a couple of you guys gotta do me a little bit of fair. Okay, correlation. Okay. All right. I will assume then you guys are you guys talking? You're talking about in relation to a scatter plot, I imagine. Would I be correct in saying that? Because usually when I think of correlation, that's usually where my mind goes, trying to relate to that. So just check me if I'm correct on that. Multiplication rule. Okay, wait, hold on one second here. Okay.
Enjoy this unicorn dancing.
Sometimes what? Chill there. Sometimes when let me see.
Oh wait, no. It won't just
oh no! What are you doing? What are you doing? I just see. Okay, statistical review. Okay. This is a. Oh wait. Wait. Am I talking about scatter plot or no? No, wait. Because when you said multiply rule, and I started looking that up, it's talking.
Plushie dance party.
Oh, jeez.
Plushie dance party.
Okay, because all right, but you are talking about scatter plots. Okay,
Yes,
all right.
Push it. Ah.
Okay, so all right. I'm gonna personally admit when it comes to scatter plots. Okay, I have not done them very often within because usually I'll admit in my past experience, because just to give you guys a little bit of background, anybody else that's watching out there, I've been teaching mathematics now for it's gonna be 19 years that I'm wrapping up so far to this point, and during my time, I usually have not been teaching the higher level maths. I have at different points in my career, but I usually haven't done algebra 2 and beyond that very often. It just hasn't come up on my plate in my years or whatever. So from that from that circumstance there, yes, I'm reading. Yes, I'm watching. Okay, so the question of scatter plots, we haven't done it very often, but like, okay, so I'm gonna do the best I can with this because, and if my explanation for the moment is is a little bit weird or off or whatever the case is, I'll make sure I get it fixed proper for the next time, because I know that this is one of those that there's a lot of calculations that are involved with it. I know that full out, and it gets, when you're trying to do it by hand, yes, it becomes very extremely complicated. I will not deny that. All right. The one thing I do definitely know for certain, without any kinds of without any looking up any sort of thing or whatever the case is. Okay, you guys are talking about a scatter plot. Just like I said, just let me know if I'm off your wavelength and not describing the thing that you want me to. Just let me know here, okay? Because I want to make sure I'm doing right by you guys and giving you the explanation of the thing it is that you want to know there. Okay, so all right, how many points I got here? That's 9. Okay, let me throw one more in. Okay, how's about that? Okay, so all right, so the whole idea here is that, okay, you've got. All right, I'm going to describe this in as general terms as I can first and stuff like that. Okay, I appreciate that. Thank you. Yeah. Yes. Like I said, sometimes, occasionally, if there's something I haven't worked on in a long time or whatever, I know the general details, but I might just have to look something up just to remind myself about if there's a rule that I'm missing or something like that. But let me give you I appreciate it. Thank you so much, guys. Okay. So let me give you the general details first there, just so you understand the kind of thing it is.
Big Dipper because you're drawing constellation.
Well, it's not really. Well, it's not a constellation kind of thing, or whatever. Huh? Although, if you wanted to, if you want,
right here it shows you could make it with the Dipper again.
I guess you kind of could there.
See, Big Dipper.
So, where's Mabel though?
Seriously, is Mabel gonna just get away?
No, don't you dare say that.
I said stop.
She likes Gravity Falls, so among other things. So get a little bit of a joke there. If we're gonna talk about Dipper, we gotta give Mabel her time, even though she probably doesn't deserve it. But anyway, here's the point about the correlation. All right, now Brianna, here's what I'm gonna ask you. As you look at this group of points, now normally when we're looking at the graph of a list of points, we're usually trying to see that all the points are in some kind of a straight. I'm actually in New Jersey, so very condensed state or whatever. So we're trying to. Expand things. However, I'll tell you the truth. I've only really gotten super hardcore with trying to build and expand the channel here over the since last summer or whatever, because I've had this channel for a few years now, but there was a long time that I hadn't done anything with it. So, but now this past year, I'm really trying to build it up. We got a little slowed down over the winter and the spring or whatever, but we've been trying to get things back going within this within doing these live streams because of all of the distance because of all the distance learning and stuff like that we've had to do. So, but I'm going to be getting some regular videos up back and going very soon. All right. So anyway, so as you look at it here, maybe, perhaps, no, I see his question too. I'm answering that well. Perhaps one day, yeah, see the USA and all that business. All right. So here, Brianna, here's what I want to know. Taking a look at these points. Now, usually when we see graphs of points, usually our ultimate goal is that we want to try to see a group of points that are traveling in a straight line like this or whatever. Now, when we see a linear equation completely like this, Brianna, that's a perfect graph. That's what we want to see. This is the type of graph that would be considered as having a 100%. Yeah, yes. No, I agree with you. Yeah, well, trying to do it by hand definitely is. This is definitely one of those topics that if you have a graphing calculator like a TI-84 or something like that, that could help organize all the complicated calculations for you. It's definitely of important use. But even then, you got to make sure you enter all the data in its proper places here. So, but the idea is that what the correlation essentially represents is how close the points are together in terms of being able to make a straight 100% linear equation. All right. So if you got if all these points perfectly lines up straight, that would be considered a 100%. And let me ask you this, Brianna, as you look from left to right, are the points rising or falling in general?
Rising.
Okay, so would that be considered a positive correlation or a negative correlation?
That's good.
Well, is it positive or negative?
Positive.
It's a positive correlation. So if you have one that's
And
perfectly
since
going
positive is related with green, pickle is green.
Here you are.
Pickle the dinosaur.
Okay. So anytime you got a perfect straight line, that would represent that. Now these points obviously do not make a straight line. So that means that while they are still going upward and the correlation is still positive, it's obviously not going to be totally 100%, or usually the way correlations are normally given. Correlations are usually established as somewhere in between negative 1.0, which means you have a negative slope of points in a perfect straight line, versus 1.00, which is a positive slope in a perfectly straight line. So correlation will always fall somewhere in that idea. The main point is that the closer that the points are to being in a straight line, the higher the value of correlation is going to be toward either +1 or -1. So that's in general how you have to look at it. Now, the biggest challenge of all, the first big hurdle that you have to get past with this stuff is you got to find what is considered the line of best fit. You got to try to be able to draw a line through these points that travels in the same general direction as the points do, and it takes the points and it splits them 50-50, half on one side of the line, half on the other, and at about equal distance to each other. It's difficult to eye it by hand, but usually if you are trying to do it by hand, usually the best advice I could give when you're trying to come up with it just on plain sight is to try to find, as you look at the points, try to look at them from some kind of a vertical standpoint. So you got to literally tilt your perspective, as it were. All right. And then as you look at the points, you got to try to see if you can find a pair of points that are in some way, shape, or form kind of like in the middle, in the direct middle of the whole thing. So like, let me see if I can figure it out from the ones that I wrote here. I'll admit, it's not a perfect science, okay? And sometimes you're not going to be totally able to get it to be 50-50. All right. All right, but how do you know how you have to draw that line? Well, like I said, yeah, it's like I said, it's never going to be it's never going to be totally perfect when you're trying to just do it plain on site and things like that. So it's like I said, so like consider this. As I look at this group of points, for example, okay, to my best estimation, because now understand, I came up with all these points like totally just on the fly for myself, and they've all got their coordinates, which I'll get to in a second. But let's suppose that I drew the line that passed. Let's see which one's going to do. I'm going to try, just for argument's sake. Okay, I'm going to try this point here, and I'm going to try to go with it. Okay, I'm going to try the far one all the way at the end. Okay, so so my straight edge, okay, now I don't have a yardstick or anything on me at this immediate moment, so just understand this is going to be, so ignore the artistic imperfection of this. I strongly recommend if you're trying to make this up by hands, have some kind of a ruler or a straight edge handy. Make sure that all these marks are evenly spaced. Oh, you have one.
There's
Okay.
actually one right
Oh, no, I didn't see him. Thank you. She saves the day. Ta-da! Okay, so,
Another one, but I think I put it
okay. It's a little short, but I'll play along with it as best I can there. So the general idea would be, okay, so we draw the line passing through. Okay, I'm gonna sort of ad-lib this here. Okay, and then take it all the way through like so there and stuff like that. Okay, so this is give or take. That's about where it is. Okay, now so let's see. So if I look at where the rest of the points are, okay, it's a little bit off, sort of, because I've got 5 of the remaining points are above the line, and I've only got 3 underneath. So I mean, it doesn't totally seem like it's 50-50, but at least but one thing that we can possibly use to kind of compensate for that argument is that, like, if you look at these 5 points, they're all like really close to the line. These 2 are also, but this one's a bit further away there. So the fact that this one's further away, this far away point could sort of count like 2 of these close ones do. So it sort of rebalances the argument. Okay. Again, it's gonna be, when you're trying to make it up yourself, it's gonna be your own yeah, everybody's going to perhaps have a slightly different interpretation. The goal is, when you're trying to make it up by hand, try to split it up 50-50 as best as you possibly can. And then if you do have a graphing calculator available to you, what would definitely be a good idea is to try to see what equation line it gives and see how close it is to yours. Now, as far as coming up with what the equation line for this is, let's take a look at the 2 points that we've got here. So this point xy is 2, and this one I've got away here. I know from the tags I wrote that's 10-6. Okay, so if I came up with a slope-intercept equation that built off of them, okay, so let's just see what we get here. All right, so for the slope, okay, we know we have to do rise over run. I think we've talked about that before in previous streams, or in case we haven't, we'll get it now. Okay, slope is based on the differences in the y coordinates, or the rise of the line, versus the difference in the x, or the run of the line. So if we plug the numbers in, we have our y's are 6 and 2 on top versus 10 and 2 on the bottom. Okay, so then we get 6 minus 2 is 4, 10 minus 2 is 8. We divide that. Okay, so the slope is 1/2. Okay, and then from there we have to come up with the y-intercept of the line. Where does it touch the y-axis? Because then that will complete our slope-intercept equation, the old-fashioned y equals mx plus b. Hopefully it's familiar to you guys right there. Okay, so the half would go right there. Now it's a matter of coming up with the b. The way I do that is I have the 1/2 right there. I'm solving for b. I have to use the x and y from one of those 2 points to try to solve for x. So let's say, for instance, I use the 10 and the 6. The 10 is the x, so that's going to go there. The y is the 6, so that's going to go there. Okay, so real quick, Brianna, half of 10. Half of 10. Okay, so half of 10 is 5, so 5 plus b equals 6. Solve for b. What do I do with that 5? How do we get rid of it?
Subtract.
Okay, so minus the 5 over, so that
Oh
means
gosh, Dad, I have to erase this.
so B has a value of okay, just relax there. B has a value of
1.
1. Okay, so with that and the slope you got, so we're estimating for ourselves, okay, again, this is by hand. The real line of best fit may be a little bit different from this, but this is a reasonable close guess. Our line of best fit would be, in this case, y equals half x plus 1.
Okay, seriously,
So-
I think I have to erase this.
So when you're trying to come up with the correlation, the first mission is to try to get a reasonable idea of where that line of best fit is supposed to be. So we're estimating that's the equation. Now that's the simple half to it, is to come up with that. If trying to guesstimate that can be called simple, I understand completely if that's already a throw off. Okay, now I will admit now at this point that doing the next layer of the problem, this is a part I have not done in forever. It's been a very, very long time. But I know that it's going to be in some way related to trying to figure out the perpendicular distance that each of these points are from the actual line of best fit, and trying to come up with some variances and stuff like that. So I just want to make sure that I am seeing this in its proper fashion here. And let me see. I gotta look at this here for a second. Okay, so aha. Okay, that's what I thought. Okay, so all right. Like I said, it's been a long time since I've looked at these formulas over. Okay, all right. Okay, all right, let's go here. I'll tell you what. I'll make you guys a promise, okay? Because all right, I mean, check me first that you understand this much. If you're trying to do it by hand, you just check me that you understand this much. All right, just let me know if that's the case. All right, because again, ultimately, when you do all the other calculations and all the other business like that, all right, one thing you're ultimately gonna understand is that, again, when you come up with the ultimate calculation. Oh, cool, thank you. So one of the things you're definitely going to see is that, like I said at the beginning, the closer that all the points as a group sit compared to where the line of best fit is, the higher a correlation value that you're going to have. So it's going to be closer to either +1 if it's traveling in an upward direction, or closer to -1 if it's traveling in a negative slope. The closer it is to 0, then the more scattered and rounded that the points are, and stuff like that. So like I said, so just to give you some base comparisons and stuff like that of some different correlations. Okay, this is just a general idea here. Okay. So just to give you some ideas. So like I said, I talked before about like I said, if you have a group of points that's traveling in a perfect straight line there, okay, so that one would have a correlation of +1.0, perfect straight line like that. Now the thing is, if they start getting a little bit scattered, okay, but they're still like tightly packed together, that there's some kind of straight line that they're all really close to, it's going to still have a high coefficient, okay? It's still going to have a high correlation coefficient. It's not going to be 1 perfectly because they're not all staying in line. But like maybe this one might, for instance, when you do all the necessary calculations, maybe it has a positive correlation of maybe 0.85 or something like that, perhaps, maybe. I don't know. Again, I'm just shooting an example there. And the further away the points get, this starts to get lower, or more specifically, it starts getting closer to 0. So like if they start getting a little more spread out like this, okay, they're still moving in an upward direction, but now it's like, okay, if you pass the line of best fit through the middle, now you can see they're starting to spread out a little bit. They're a little more, it's a little more rounded. So the correlation is going to get to be a little lower. Like maybe the correlation in this is only a 0.40, for example, because they're starting to balloon a little bit, you know? And then the worst possible example, okay, for you to have a zero correlation, for the points that have no correlation at all whatsoever, or whatever the case is, you'd pretty much have to see something that's kind of like this, where the points are kind of like almost literally just like in a random clump that are in such a random clump that it's like it's almost practically like a circle and stuff like that. There's no definite direction to the points. There's no identifiable slope scheme or whatever the case is like that or whatever. So in a circumstance like this or whatever, any attempt to try to draw a line of best fit is going to really just be, just random, a random crapshoot or whatever the case is in that. So this is going to be the kind of one that's going to have a correlation of closer to zero or no relationship at all. Because another part of the whole correlation discussion is the nature that you're trying to say, what is Y doing as X does this, okay? So, and the closer that the correlation is to a positive one or to a negative one, it tells you exactly that, like in a positive one situation is that Y would increase by this exact amount as X increases by this exact amount. That's what a perfect positive correlation would say. And a perfect negative correlation of -1 would say the same thing. Y decreases by this exact amount, while X increases by this exact amount, okay? And the closer the correlate, and the lower the correlation gets, or the closer it gets to zero from either end, you can't say it exactly does this. You have to say it moves at about this rate for between the X's and the Y's and stuff like that. When you have a zero correlation, it's saying that there is no calculable way of identifying how Y is behaving versus how X is behaving. So that's the nature of that. Okay, so that gives you the general idea of like how to read what the correlation numbers, what they represent in terms of the scheme of how spread out and how balloons the points in a scatter plot happen to read or whatever. As far as the by hand calculations, I'll make sure for Tuesday I'll take for the one I created. I'll see if I can take a swing at it again and just remind myself of the kind of calculations necessary. I'm pretty sure I know what to do because I think I was just doing something that was similar to that from a statistics standpoint. Because my guys are working on standard deviation this week, and I think it sort of plays along that line. But let me have a look at it over the weekends, and I'll get back to you guys and see what the story is on that. Okay, so we'll pick. So this conversation is to be continued, if that's all right there. All right, so we got all that in perspective. And I thank you guys, for your questions. Though, no, it's I appreciate your getting there. Just out of curiosity, any of you guys have any younger siblings and stuff like that or whatever? Because I just want to make sure I give open opportunity to any of the lower grades to be able to get their discussions in. So I'm just curious if you guys have any younger siblings or anything like that or whatever that are having any math troubles on their own ends and stuff like that. So what was that?
What?
Joey's studying upstairs again. Oh, okay, cool. Oh, cool. What grade is she in? What grade is she in, Luke? I'd be curious there. So, yeah, because like I said, I get hit.
What is up, my math student?
Yes, we had visitors, Joe.
What?
Hans is back and he brought friends. So
Joey, what?
he said, "What's up, my math students?"
I know. I'm just like, what's up, my math student? arguments again.
Yes,
Stop.
Yes, there's Joey or whatever. So you've met the whole family now or whatever. And said, well, here, wait. I don't think Brianna was quite on screen. Peek your head in because they didn't see
Hi.
you. There's Brianna. Okay. I personally don't watch that show. I will admit I've heard of it. I've seen it or whatever.
I think Mommy does.
I don't think Mommy watches Grey's Anatomy. I know my mom's watched it, but
She might. I don't know. I've just seen it on Hulu.
I understand.
Like I
yeah.
haven't. Of course.
I would admit, Medicine in the Doctor's Room is those kind of shows that have always I'm like irked out by that kind of stuff or whatever. So like I know my parents were big on shows in the 90s like ER and Chicago Hope and stuff like that. They were big fans of those. I couldn't get into those. Even there's a newer show that just came on the last couple of years called The Good Doctor. I looked at an episode or two of it. I mean, I thought it was okay, but it's like I couldn't get into it all that much. I will personally admit, just so you guys are aware, I personally my specialty genre when it comes to television, I'm a huge game show nut. I'm big on that sort of thing and stuff like that. So so a lot of those kind of shows I'm really big with. My favorite all time is
I like cartoons.
yeah, well gee, you're 11. I would hope cartoons you like there or whatever. But my big favorite of all time, I don't know if you guys are familiar with it at all. If you've ever heard of a game show called Press Your Luck. I don't know if you guys know that one over there in the Netherlands. I know there is another show that's been popular in the States here for a number of years. It had a good run for a while, and I know that you would probably know because it was a big hit in the Netherlands. You guys would probably know. Okay, you're not familiar. All right, I'll tell you about Press Your Luck in a minute or whatever.
I'm trying to think. Whammy.
The biggest. That is not what a whammy looks like.
I forget what a whammy looks like.
Oh dear God.
It looks more like Swiper from Dora.
Not even.
I don't know what that is.
That looks.
I don't know.
That looks like a rebellious sunflower. Get me out of this garden in a hurry.
What does a whammy look like again?
Here, I'm gonna show
Is it
them.
like this?
I'm gonna show them real fast.
There we go.
I know what it looks like. Give me a second here.
There we go. There we go. I fixed it.
Oh, you guys are nuts.
There we go. I fixed it.
You guys are nuts. Okay, yeah.
It.
That's not even what he looks like. This no, okay. So that you have an understanding, okay. All right. What she's trying to draw is this guy, okay?
See, doesn't that look exactly like him?
No.
Wait, I just forgot some details. There we go. Now it looks exactly like.
You got some work to do, but yeah, thank you, I appreciate it. But yeah, this is the way. Oh, okay. my friend Scott has chimed in there, but yeah, this is the whammy. He is the villain of the game show Press Your Luck, because the whole basic idea here. I'll cue up
This is the best
I'll cue up
ever.
the graphics so that you have an understanding of kind of what it looks like. Is that you've got a setup
This
where
is the most perfect whammy
where you got a board that has like a rotating series of money and prizes on it and stuff like that. Okay, and the whole idea is that you've got to press a button in order to stop the board, and whatever it lands on, that determines what it is that you win and stuff like that. Okay.
Yes, red feet.
So the board looks something.
Dad, I fixed him up.
Okay. So the board looks something like this. So you see an 18. So you see a board of 18 squares like that, and there would be a light bouncing around the board and stuff like that. And wherever you stop the light, that determines what you win. If you land on one of those whammies, then you lose all your money. and you
Look,
get
he told me
subject to
some
some
money.
kind of cartoon humiliation, stuff like
Look,
that.
he's
So
taking
that's
some money.
that's like the big show that I've always been a fan of and stuff like that.
It's
I
a
know you
whammy.
don't think of him as a villain, Scott, but to the players trying to win all the money, they think of him as. So that's the
He's
kind of thing
cute.
there.
Look, he has money. He took the money.
Of course he does.
And look,
That's his job.
Isn't that a great whammy drawing?
I very much appreciate it and stuff like that, however. And I'm gonna tell you this. As a matter of fact, one other thing, Hans, real quick before we sign off here today. And actually, I want to build this off of something that you were doing earlier in the week, not for math, but that you were doing for your English assignments this week. Because the thing you were doing for your English things is actually a mathematical concept.
Really?
And it's actually, Hans, something that I'm in the middle of trying to put I'm trying to put a song together for this, okay? And the song and no, not that one. Not that one. No, not that one. Not that one. Something else.
Oh, I can draw SpongeBob.
You remember in your English assignments this week, remember you were doing
Venn diagram.
Right. You were doing the Venn diagrams, trying to compare and contrast different elements and to find out what it is that they have in common. Man, move over a second. I got to explain this real fast.
I can definitely draw SpongeBob.
Hello.
Can I draw SpongeBob?
Fine. Okay. But no, what I'm trying to do is because she was doing stuff in her English reports this week, or whatever. She's reading 2 different fables, and she had to compare the main characters and stuff like that in the different circumstances. Like what were 2 of the stories that what were the first 2 we had to do this week, just for example?
The golden goose and
That's right. We had to do the goose that laid the golden egg and the fox and the grapes. And she had to determine she had to determine like what the 2 stories had in common in terms of their characters. That would be what would go in this area in between, because in each individual circle, okay, you have the number of items, or from a qualitative perspective, the number of facts that are there about one story. So you have your facts about one thing, and in the other bubble you have your facts about the other one. And the whole idea is that the area in the middle would summarize the facts that are there about both of them. Okay, this is what that area is, what is referred to as the intersection of the two. The intersection of the two.
How about
the 2 areas of facts and stuff like that.
SpongeBob and Whammy.
Well, not right now. We're not going to do that at this immediate second.
I know something.
But the thing is that based on the general things and the kind of the basic calculations that you have to do with when you have numbers in a Venn diagram, I'm trying to build a song around that and stuff like that. I've got the verses mostly done. But I've just gotta finish the last verse and just try to get it in place, however. And then ultimately, once I've got the verses in place, I'm gonna try to see if I can put it to animation, because there's a song that I want to use that I'm basing the lyrics around to cover the concept of the Venn diagram. And actually, my wife, who you saw on the show today's episode earlier today, Hey, wait a minute. You've heard me sing. You've heard me sing, Scott. You know I sing okay. All right. I'm kind of a Billy Joel style singer, but no. But actually, this is one that actually Andrea's going to sing it, because it's a female lead for the song or whatever, and it's it's kind of a ballady type of song and stuff like that. So her voice is much more suited to it than I am and stuff like that. So that's the so I'm gonna have her sing it, and we'll have the animation play in the background stuff. And hopefully, when we ultimately get this done, I'm gonna try real hard to get it done over the summer. I promise you guys are gonna like it, and I hope you guys spread it around and make it a big, huge hit, because I don't know that anybody's ever done a song about Venn diagrams and done this with the song that I plan to use. I'm not going to say what it is, okay, because I want this to be a surprise. So just think about it, and we'll talk about more later on. But so
oh gosh, talk.
Everybody's got their opinions. Like I said, stay out of that stuff because I hate them all.
He
So,
has a lot of hair.
huh?
Like,
Or so he thinks he has a lot of hair.
No, but I've seen an animation
Everybody.
called Trump's on Mars, and I think they animated him with the biggest hair.
Oh, everybody does. Everybody gives him the pompadour from the 50s and stuff like that because that's the only way they can characterize him. Who knows? But
it's a wall.
Huh?
It's a wall.
I think he's talking about the.
I know, but it's a wall. That's why I think about walls. They're walls.
I honestly, I couldn't tell you one way or another. It's there. That's all I could really say.
It just exists.
Say one way or another. There's some parts of, and this is why I stay out of politics because there's so much about what they want. And you know what? Here, wait. From a perspective of a Venn diagram, think about this. Okay, this is mainly the reason why I hate conversations about politics, so much, or that I hate most politicians in general. Because think about, not in Jersey. No, today we've been the last couple of weeks we've been stuck in the 50s, maybe low 60s. We spiked. We're at 85 today in Jersey. It's crazy. We're sweating a little here. But here, perfect example. Okay, from a Venn diagram perspective. Okay, you have what the Democrats like. And want to do, and what the Republicans like, and what they want to do with this country. And here's the problem. Here's what
I can't agree on a single thing.
Yeah. You know, they have all their stuff that they like and want to do.
They have all their stuff.
And guess what's here in the middle?
Nothing.
Nada. Nothing. It's an empty set. There is no overlap or whatever. Or if there is, it's so small that it's completely irrelevant and stuff like that. So it's really, I have no clue whatsoever that it's and the whole point is that they're supposed to be working together. Yeah, exact. Thank you. Yes, Scott said it perfectly. It's the whole Willy Wonka. You get nothing. You lose. Good day, sir. Yes, exactly. Thank you, Scott.
This is what I wrote.
So,
well, nothing in here.
Yes, nothing in here. Exactly. So, I mean, that's what drives me nuts about politics, that there's no agreement. There's very few, if any, laws that are ever written that are honestly a collaboration by both parties, or there used to be, but they don't exist anymore. Or if they do, good luck trying to find them. But that's, I don't know. That's the problem that I have and stuff like that. So any political discussion, it's I see one side's argument, I see the other side's argument. I try to think who's got it more right, but there's very little that they ever agree upon. It drives me crazy. All right.
I've never left.
Yeah, I can. Yeah, obviously you haven't, but no, neither have I to this point or whatever. I know my friend Scott's. I know my friend Scott said he wants to visit Japan one day when all of this is done and stuff like that. poor Scott, your trip to Japan keeps getting delayed further and further.
Yeah.
Because I think, what is it? Didn't you tell me, Scott, that you wanted to go to Japan like a couple of years ago, over Christmas 2018 or 2017, and then it got delayed to 18, 19, and now who knows when you're going to be able to go, right? So. Beats the heck out of me, but
I'm just excited for.
Be that as it may, okay. So anyway, you're still planning on going in December, Scott? Oh wow. Okay. I hope that a lot of this stuff. I hope a lot of this stuff is worked out a little bit better and stuff like that, because I literally just read last night. I thought that they were trying to slowly reopen Japan, and I think the cases started spiking again, which obviously it's going to do that a little bit. You're not going to be able to totally avoid, until we have the vaccine, obviously, and this is true everywhere, you're not going to be able to totally get everything to just not happen anymore, when we reopen. So everybody, bottom line, we're all doing the best that we can here. I hope you guys are doing okay. We're doing what we can. Again, regardless of how government is handling it, good, bad, or whatever the case is. No, he's not family. He's a good yet crazy, and sometimes for what he wants, very pushy friends of mine and stuff like that.
Hey.
He means well. He tries way too hard sometimes. Okay, and he knows it. So so be that as it may. But so anyway, but that's the story out there. But I hope that you guys are doing okay. I hope everybody watching this is doing okay. All right. For now, though, we're gonna cut out of here
What about the game?
just for right now. Okay. All right. Well, we ran a little bit out of time for games and stuff like that. But I'll tell you what. Even I'll go so far as this. Okay.
What games Monday?
Well, not Monday. Okay. Well, here I'm gonna make sure that next week, okay, we're gonna do three broadcasts next week, because next week is our as I mentioned before, next week is our last planned week of doing these live streams for a moment. And again, it's only because of the fact that here in the States there's a lot of hold on, let me finish what I'm saying. Because,
Ooh, raining plushies. Ooh, raining plushies. Ooh.
she's gonna do this until she takes an eye out.
Raining plushies.
But anyway, we're gonna do three broadcasts next week. Because okay, can you chill? Can I talk here? All right, Brianna, can I talk here, please? Can I talk? Everybody's a comedian. But anyway, so here's what we're gonna do yeah, exactly. So we're gonna do three shows next week to close out. We're gonna do a standard broadcast like we did today with your math topics and stuff like that. We're gonna do one. We'll do it on Tuesday and we'll do it on Thursday, and then for Friday to close this out or whatever, we're gonna do a whole hour, maybe two, depending on the circumstances. We're gonna do a whole fun and games Friday to close out as we go into Memorial Day weekend and stuff like that. And again, the reason why we're closing it off next week is because I know that a lot of schools around here in the States, depending on where you live in the country, some states their school year is either ending either right now or close to right now within the next week or two, whatever. Some like here in Jersey, like a lot of the Midwest states and stuff like that are just about closing and stuff like that and things. Okay, enough. Come on, let me talk.
Jeez.
Enough.
Okay,
Quit interrupting. But now I know, we here in Jersey, we go longer. I know that here in Jersey we do it longer because of
September to
because we usually end in like mid to late June, stuff like that, and some schools around this area do. Everybody's different, but given that we want to make sure that we're trying to hit as many people as possible and be able to have everybody play along or whatever. So we're gonna play along to the early end dates or whatever. So that's why next week is gonna be our last week doing these. But we're gonna have three shows just to be able to let everybody squeeze in. So please come on back on Tuesday, on Thursday, and then come join us and play along live in the chat for our fun and games Friday. Hopefully we're gonna have a big blast here with all of our math games that we talked about. And there's the phone. I gotta get that. We'll see you guys on Tuesday at 2 p.m. New York time. Take care. See ya. Sort of, I think. Why isn't the button working? There it is. Okay, we'll see you soon.